got all the time afterwards. So next up, we have our very own Vice President, Jazmin. She started her PhD after a 3-year BSc here at the University of Leicester. Jazmin's supervisors are Professor John Lappington and Dr. Steve Leach, and she's now working with the Southern Widefield Gamma Ray Observatory, designing photodetector prototypes with wavelength shifting materials using Monte Carlo simulations. So over to you, Jazmin. Every second, Earth is bombarded by high-energy cosmic and gamma rays. But where are these rays coming from, and what information can they tell us? Well, by detecting these rays, we can build up a sky map of transient and variable multi-wavelength and multi-messenger phenomena through mapping large-scale emissions. Now, this sky map up here was taken by the NASA Fermi Space Telescope from the energy ranges of about 8 kiloelectron volts to 300 gigaelectron volts. Now, how can we replicate this at much higher energies and from the comfort of the ground? Well, a water Cherenkov detector is one method of ground-based detection used to map gamma ray emissions like this. Now, the high-altitude water Cherenkov Gamma Ray Observatory, also known as HAWK, is one example already doing this in the Northern Hemisphere. But as depicted by the map above, it can't yet see the entire sky and has some blind spots. So a new concept, the Southern Widefield Gamma Ray Observatory, known as SWGO, is doing this in the Southern Hemisphere, or will be doing this in the Southern Hemisphere, and have a much wider field of view and be more sensitive than HAWK. So it will be able to complement the work HAWK is doing and see the blind spots HAWK cannot, including the galactic center. So what is SWGO and how does a water Cherenkov detector work? Well, SWGO will be consisted of an array of water Cherenkov tanks located in South America at an altitude of about 4.4 kilometers or higher. And a water Cherenkov detector works by detecting the Cherenkov radiation emitted by high-energy secondary particles, which are a product of cosmic and gamma ray-induced particle showers in our atmosphere. Now, Cherenkov radiation is induced when a high-energy particle reaches speeds faster than the local speed of light in a dielectric medium, such as water. And Cherenkov radiation is emitted in a cone-like shape. So by analysing those photons, we can determine the direction and energy of the particles, hence enabling us to determine the gamma ray source and build up a sky map. So where does my research come in? So I'm using Monte Carlo simulations to develop and model a photodetector prototype for a water Cherenkov tank, to using wavelength shifting materials to improve the photodetector efficiency. So figure 3 here is a 3-inch photomultiplier tube embedded in a wavelength shifting slab. And now, while some of the Cherenkov radiation is directly detected by the PMT, the rest, which would usually be lost, is detected later through the wavelength shifting material. So research like this is vital to new and small groups like SWGO, because if I can prove that my prototype and model works, they can use much smaller sized PMTs, therefore saving them lots of money in the future, and it can be used for other areas of research. Thank you very much. Any questions? Oh, thanks. Any questions? Cool. You can talk to me later. Thank you.